Okay, the next one for figuring out Lewis structures and all of this detailed information that goes along with it, these properties of the molecule would be XeF4. For this one, we would start out again by counting the number of valence electrons. We get 8 from xenon and 28 total from the fluorine. So that's a total of 36 when I add it up. Arranging the atoms symmetrically on my piece of paper, I would get something maybe look like this. And then the next thing that I would do would be to draw one single bond between each of the atoms and the central atom. Okay, so I subtract the 8 electrons that were in those 4 bonds, and I would be left with 28 electrons. Giving everything else octets, I would end up with a structure that looked like this, but then I would have 2 electrons left over. So I would use 24 and I would have 4 electrons left over. Okay, xenon is something that can do an expanded octet. So I would just take those leftover 4 electrons and make an expanded octet by putting 2 lone pairs around xenon. So now it's time to figure out the electron geometry. The electron geometry will be based on the 6 geometry groups. I have 4 bonds to fluorine, so that's 1, 2, 3, 4 geometry groups, and then I have 2 lone pairs. That's a total of 6 electron groups or geometry groups, and that means it's octahedral electron geometry. With 2 lone pairs, that octahedral electron geometry represents a molecular geometry of square planar. So the shape that only the atoms make is a square plane. And that brings us to the bond angles. The bond angles for all octahedral structures are simply 90 degrees. Now, we're going to show you the square plane here in just a second. And we're going to do that when we talk about whether the molecule is polar or nonpolar. Now, this is an example of if you use the quick and dirty rule that says if all of the geometry groups are identical, then the molecule is nonpolar. But if the geometry groups are not identical, then it's polar. And so bonds to fluorine is not the same as lone pair. So you might say polar, but in fact, the molecule is nonpolar. And the reason is that polarity has to do with molecular symmetry, and it really has to do whether or not bond dipoles cancel. So let's take a look at this square planar geometry. Here are the 4 bonds to fluorine oriented in a square plane, but I've got the 2 lone pairs oriented 90 degrees from that plane. And so this means when I take a look at all of the bond dipole moments, they're all pointing in equal and opposite directions, so they cancel out. And the dipole moments created by the electrons, since they're directly across from each other 180 degrees, also cancel out. And so that means the molecule is overall non-polar. And so again, remember, the quick and dirty rule is going to get you right most of the time, but sometimes it'll steer you in the wrong directions. This is one of those examples. So xenon tetrafluoride is in fact non-polar, which means the intermolecular forces are dispersion only. The hybridization will always be determined based on the electron geometry. In this case, octahedral, that means sp3d2 hybridization. All single bonds, those are sigma, and there's 4 of them. And that means there's no pi bonds because there's no double or triple bonds. And that's xenon tetrafluoride.